Morning, nerds. Today we are getting to actual trigonometry, actual trig. Because starting today, we are no longer stuck in quadrant 1. We can go to any quadrant we want. That knowledge begins with some vocabulary. And the vocabulary is another co-word, another word that begins with CO. We talked about co, the prefix co meaning together. Co-terminal angles are angles that terminate, meaning to end, in the same place. Okay? We've already talked about what it means to be an initial side and a terminal side, but I'm going to go ahead and say it again. The initial side of an angle will always be on the positive x-axis, and the terminal side of an angle is just where the angle ended. It's just the other ray. That's the terminal side. Okay? So coterminal angles are angles that terminate, meaning to end, angles that end in the exact same place in space. I mean, the thing is there's only so far you could go in a circle, right? But, you know, you can continue to spin and you have gone through more degrees than what your circle had to offer. Now, it's not going to work in the video, but, you know, if I'm sitting here looking at Jared and I say, Jared's directly in front of me, so he is 0 degrees from me. Yes? But I could turn this chair in a circle, whee, and I could stop and I could be looking at Jared again. And obviously, I moved. Therefore, the two angles are not the same. One was 0 and one was 360 degrees or 2 pi radians. But since I ended in the exact same spot, I would say that those two angles are coterminal. Okay? So every angle has an infinite number of coterminal angles. Just keep turning full circles. And you could actually turn full circles positive or full circles negative. I mentioned this yesterday, but here it is in an image. Angles that open counterclockwise from the positive x-axis are doing what they should. Those would be positive angles. Angles that start at the positive x-axis but then go clockwise would be negative. So I mentioned that yesterday. There it is again. Here it is with the picture. So this little arrow is telling me which way angle alpha opened. Counterclockwise, angle alpha is positive. This little arrow is showing me which way angle beta opened. Clockwise, angle beta is negative. Okay? This third image shows one pair of initial and terminal sides, but it's showing two different angles. Angle alpha is acute. It goes from 0 to, well, here. That kind of looks like 45 degrees, right? So let's just say, for the sake of argument, let's say angle alpha is 45 degrees. Pi over 4 radians. Angle beta traveled the initial 45 degrees, pi over 4 radians, and then for the fun of it decided to turn another full circle. You see, turning a full circle does nothing. It puts you back in the exact same spot, bless you. It puts you back in the exact same spot. And since it was a counterclockwise circle, that's a positive circle. So angle beta then would be the initial 45 degrees that angle alpha went through, and then, oh, that's orange. I meant to write that in red. And then for the thrill of it, turned another full circle. So angle beta has a measure of 405 degrees. Again, that's if we assume angle alpha was 45 degrees. And, you know, angle beta didn't have to turn the full positive circle. It could have turned a full negative circle. Still been coterminal, and would have had a different angle measurement. It would have been negative 315 degrees. And we'll practice doing that in a minute. Here, I have angle alpha and beta being coterminal to one another again. One of them is positive, one of them is negative. But you see, they both create this initial side and this terminal side. So when we start doing trigonometry all over the world, trig of angle A is equal to trig of angle B because it's the same point in space, even though the angles themselves are different. Cool with that idea? Okay. Vocabulary for you that you are not going to be held responsible for, but you might as well know in case you want to ask, you might as well hear it now. Notice that these two angles together, if they were both positive, would build a circle, right? Okay, but they're not both positive. So when they're not both positive, we can't say they add up to 360 because they don't. They don't add up to 360. But there's still a word for an angle like this and this that are coterminal that, when put together, build a whole circle. They're called reflex angles. You will not be held responsible to know that word. I just figured I'd tell you. And two positive angles that add up to 360, there is a vocabulary word for that, that once again I will not hold you responsible for. So complementary angles are positive that add to 90. Supplementary angles are positive that add to 180. Explementary angles are positive that add to 360. You don't have to know. But these are things that students have asked me in the past, so I've looked it up. There you go. Cool? So reflex angles are two angles that together would make a full circle. It doesn't matter if they're both positive, both negative. So like together they make a circle. It's like if you have a circle and I told you here's alpha, you'd go, oh, well, this doesn't matter positive or negative. This is the reflex angle to alpha because it just builds the rest of the circle. If I told you alpha was 100, then I go, oh, the explementary angle to 100, it's 260. But you don't need to know either of those things. I'm just a big old nerd. For these three, what we're going to do is we're going to draw, cheesy little picture not drawn to scale. It never will be. We will then find two coterminal angles to what we have. One positive, one negative. And it's extremely simple. You want a positive coterminal angle to where you already are? Add 360 if it's degrees. Add 2 pi if it's radians. If the angle's small enough and you want a negative one, fine. Subtract 360 if it's degrees. Subtract 2 pi if it's radians. That'll usually do it. But I also want the picture. Why do I need the picture if I know all I have to do is add or subtract 360? I'm going to tell you why. Because knowing where your angle is, in which quadrant, I would argue that that's half the battle for trigonometry. If you could tell me where an angle is, you already know half the information. Because the other half is, well, what kind of angle was it? Was it a 30? Was it a 60? Was it a 90? Was it a 45? If I'm asking you to do it by hand. And that's everything. So let's draw our XY axis. And remember, these are pictures not drawn to scale. Don't stress out if your picture doesn't look great. 30 degrees. I draw everything that looks like a 45 just because it makes space I can write in it. So I'll draw it in purple. And I'll do this little arrow like that. And that shows me that this thing started at 0 and opened counterclockwise like it's supposed to, and is now a 30-degree angle. Here's a coterminal angle, but it's going to be negative. I'll call that one beta. It's like a B with a little stick on the bottom of it. Let me draw the coterminal positive angle. It travels the original 30 degrees, and then, for the fun of it, spins a full circle. That one will be alpha. And it doesn't matter which one we find first. I'm still holding the blue pen, so I'll do alpha first. So alpha, I told you, it traveled the original 30 degrees, and then for fun, went another whole circle. There you go. So 390 degrees is coterminal to 30 degrees. How does that idea feel to you? Does it make sense? Imagine I was talking to you, and I spun a whole circle and kept talking to you as if nothing happened. That's alpha. Nobody seems panicked yet, so I think I'm good to keep going. By the way, do not hesitate to ask any questions at all about this material. Because we are going forward outside of our normal textbook, I'm not in a rush with any of this knowledge. I don't have a goal where like, I have to get to section 10.6. I don't really care. This is a quality versus quantity situation at this point. I need to make sure that the trig that we learn, we master. One, it's because I want you to get good test grades from me. But two, it's because eventually, as long as you further your education, you will come across trigonometry somewhere, either in this high school or SCF or at a university. Unless you're going to go to a trade school or unless you're going to graduate high school and call it quits, you're going to come across trig. And I would love to be the reason why you were good at it. Okay? So I'm not going to rush it. Everybody's cool. Yes? Okay. Beta. This is how we calculate beta. Pretend you traveled the purple 30 degrees. And then you decided to backtrack a full circle. Now, would you ever do that in reality? No. And is that what my red arrow on my picture shows? No. The red arrow on my picture shows you starting at 0 and then traveling 330 degrees in a clockwise fashion. So essentially what it did was it said, I didn't go the whole negative 360 because I didn't travel the last 30. That's what the red image shows. Because if I had traveled the last 30, I would have gone negative 360. Does that make sense? It's like I was 30 degrees before negative 360 degrees. Because 0 and negative 360 degrees are coterminal. So the arrow shows 30 degrees before negative 360. Calculation-wise, yeah, you just do 30 minus 360. And these are but two of the infinite number of correct answers. I could add 360 to this as many times as I want to, and every single time I add 360 to this, I'm in the same spot. I could subtract 360 from this as many times as I want to, and every time I do it, I'm in the same spot. And everybody's cool with that idea? Okay. Let's do another one. Remember, I told you, I believe that figuring out what quadrant you're in is half the battle. If this is 0 degrees, and it says negative, I'm going clockwise. Which quadrant would I land in if I go negative 150 degrees? If I go 150 degrees clockwise, which quadrant will I land in? 1, 2, 3, or 4? 3. Picture not drawn to scale. Oh, crap. I meant to do that in purple. Well, it's already black. Too late. Can't fix it now. Here's the negative 150 degrees. For these examples, I'm doing blue positive, red negative, but that's just me, okay? It's not like you have to, just letting you know, because I feel like color coding the notes helps. The blue positive angle, alpha, is the reflex of negative 150. Let's go ahead and calculate it. Imagine you traveled the negative 150 degrees and then thought, nah, and you turned a full positive circle. That would do this. Uh, 210 degrees? Yes? Yeah, just adding 360 gets you closer to positive. Subtracting 360 gets you closer to negative. Yeah. Well, which one is alpha, which one is beta is completely up to you. I'm choosing alpha to be positive. Like, that's not a rule anywhere. I just chose that. Because, legitimately, because that's what I saw in the picture. Not because it matters. It's just because. But yeah, just add and subtract full circles. That's all we're doing. Because adding and subtracting a full circle will never change where you were looking. Imagine you were spinning circles. In actuality, what did we do? We started at 0 and we traveled 210 positive degrees. If I'm traveling positive degrees, what is this over here? How many degrees is that? Whoop. 180, right? So how far past 180 is this angle? 30 degrees. You know what that means? I could draw a vertical line right here and I'd have a 30, 60, 90 triangle right there. And we know how to do trig in 30, 60, 90 triangles, don't we? How about that? I could do trig at an angle that is too large to even fit inside a triangle. Interesting. The negative angle, imagine we took the negative 150 degree trip and then for fun decided to spend another negative circle. Whee! The calculations are negative 150 minus 360. Negative 510 degrees. I'm going to be real with you. If you said to me, quick, oops, I forgot my negative sign. Quick, what quadrant is negative 510 degrees in? I would go, 3. See how slow that is? And the reason why is because I would legitimately have to go, okay, how far past 360 did I go? That's 150 past 360, but we're talking negative, so it's in quadrant 3. That just sucks. It's so bad. And the bigger this number gets, the worse it is. Subtract another 360. You'd be at negative 870 degrees. If I asked you, quick, where's negative 870 degrees going to land you? Wouldn't you be mad? Because they're like, now I got to work on multiples of 360, and I'm going to have to try to subtract or add, or however you like to do, minus negatives and things like that, to figure out where you landed. You know what's so much better than that? Radians. Radians are so much better than that. So much better. We got to get you used to thinking in radians, used to working in radians. Because it's the way you want to do it. Now, a moment ago, Mia asked me, can we always just add 360 and subtract 360? The answer is yes, you can, if it's in degrees. But if it's in radians, what are we adding or subtracting? 2 pi. 2 pi radians is a full circle. What's 2 pi over 3 plus 2 pi? No degrees, not allowed. Radians. Kind of a pain in the butt, isn't it? You know why it's a pain in the butt? Common denominators. That's why. So what are you going to do? You're going to start thinking of your 2 pi's as multiples of things. Multiples of thirds, multiples of sixths, multiples of fourths. Where do we want to squeeze this on our notes? How about we just run it across the top here? Start with an easy one. Let's talk money. How many quarters are there in $2? 8 quarters. 8 pi over 4 is 2 pi. Kelsey, you all right? You look like you're thinking your way through that. Okay, 8 divided by 4 is 2. Okay. What if it's thirds? 6. You guys see the pattern? 2 times 4 is 8. 2 times 3 is 6. What is it in sixths? 12. There. And you'll get used to thinking 8/4, 6/3, 12/6 for your 2 pi's. You'll just get used to it. Because yeah, we're just going to add and subtract 2 pi from this, which means I'm going to be adding and subtracting 6 pi over 3. This needed a common denominator. But we are going to draw it. I don't care if you know what the answer is without drawing it. You're going to draw it. You need to be able to draw these things. Unless you memorize the unit circle. Even then, 8 pi over 3 is not on your unit circle. So, here's 0 radians. How many radians is this? Pi radians? No, not 1 radian. It's 1 pi radians. Remember, pi is a number. So this is telling you there's a little bit more than 3 radians in this half circle. That's what that says. It's 1 pi. A little bit more than 3 radians. What's halfway between 0 and 1 pi? 1/2 pi. So we'll say pi over 2. This says 2/3 of a pi. So what quadrant is that in? Second quadrant. Because 2/3 of something is more than half of something, but it's less than 1 of something. Yes? Okay. So picture not drawn to scale. I don't actually care what it looks like. The point is, you know it's in quadrant 2. So here is your 2 pi over 3 angle. 2 pi over 3 radians. Here's its reflex. And because it's negative, I said it was beta, but that's just a me thing. It's not necessary. And let's draw its positive equivalent. So we went to 2 pi over 3, and then for fun, we decided to turn another whole circle. Man, that was fun. So yeah, angle alpha is your original 2 pi over 3 plus 2 pi. But 2 pi is 6 pi over 3. Bless you. So there it is. 8 pi over 3. What is that in degrees? I don't know. And I don't care. Because I can tell you what quadrant it's in a heartbeat. How do I know what quadrant it's in so fast? You are hopefully thinking. Here's why. 0 pi, 1 pi, 2 pi, 3 pi, 4 pi, 5 pi, over and over and over again, right? So 0, 1, 2, 3, 4, 5 pi's. Cool with that idea? 8 over 3 is almost 9 over 3. And what does 9 over 3 equal? 3. This is almost 3 pi's. So 0, 1, 2, 3. I'm not quite to 3 pi's yet. I must be in quadrant 2. It's like that. And what is 180? Notice I'm ignoring the 8. What is 180 divided by 3? 60 degrees. That's a 60-degree angle in quadrant 2. So I know where it is, and I know its size. I don't know what that is in degrees, and I don't need to. I know where it is, and I know the size of the triangle that it draws. And I could do that with any, I don't know. Someone give me a big number, a big 2-digit number. 27. So we want to say 27 over 6? Okay. 27 over 6. 6 goes into 27 4 times. This is 4 times. This is 4 pi. So it's going to leave me 4 pi over 3 remaining, which is 2 pi over 3. This is actually 27 pi over 6. It's the exact same angle. This is coterminal to 27 pi over 6. How about that? But you see how fast I was able to get there? 27 over 6 is 4 3/4. No. 4 4/6. There we go. And 4/6 reduces to 2/3. Boom, there I am. It's fast. Okay? And I didn't even reduce. 27 over 6 reduces to what? 9 over something? 27 over 6. What does it reduce to? Look, I have to write it down, is the problem. But the point is, you see how I did it? I could take any big number. 55 thirds. What quadrant is that in? Well, 3 doesn't go into 55. 3 does go into 51, though. It goes in 17 times. This is 17 pi, because this is the odd one. And the remainder will be 4 thirds, right? Oh, did I say 55? 51, it goes into 54. I'll be okay. So it's pi over 3. Boink, it's quadrant 1. And over 3, that's a 60-degree angle in quadrant 1. Like that. How many degrees is 55 pi over 3? A lot. That's how many. A lot. And if you'd asked me where that giant degree was, what quadrant it is, I would have no clue. But radians, they are our friends. Degrees are not. Okay, I'll get off that soapbox. Let's do beta. Beta is as if you decided to go the original 2 pi over 3, and then you subtracted 2 pi to get a negative number. By the way, that's 6 pi over 3. There it is. Because that is 2 pi, which is a full circle. Because this one was in thirds, so I needed to know how many thirds makes a full circle. 6 of them does. And there it is. Coterminal angles. How do you feel about that? Not bad? Not scary? You guys can find coterminal angles? Awesome! We did a question like this 2 days ago, where we had a triangle in quadrant 1. I don't think I gave it to you as a coordinate, though, an x comma y. We know that's in quadrant 1 because x and y are both positive. So I'm going to draw quadrant 1. And I'm going to tell you picture not drawn to scale because who cares? And I'm going to tell you that is the point 5 comma 3. So let me ask you, how many tick marks would have been on this x-axis right here? Oh, 5 of them. Oh, okay. And how many tick marks would have been on the y-axis? 3. Okay, well, I'll just put that 3 right here then. And I know 2 of the sides of this right triangle. How do I find the length of the hypotenuse? Pythagorean theorem. And you know what? I'm going to call that hypotenuse R. Let's do the Pythagorean theorem. Ready? 3 squared plus 5 squared equals r squared. 9 plus 25 is r squared. So r squared is 34. We take the square root of both sides to get r equals square root of 34. Oh, by the way, theta is here because it's in standard position. Standard position means starts at the x-axis and then terminates at the ray that is representing our hypotenuse. Do you think with these 3 sides now, you could do all 6 trig functions? Can you do SOHCAHTOA and the reciprocals? It's not bad, right? Because we did that the last 2 days, yes? Had a triangle, had some side lengths on it, and we did SOHCAHTOA and their reciprocals. Sine opposite over hypotenuse, so cosecant, flip it over. Cosine adjacent over hypotenuse, secant, flip it over. Tangent opposite over adjacent, cotangent, flip it over. You can pull that off, right? Awesome. Since I know you know how to do that, I'm not going to bother. Because I want to do the next question. Because you'll notice this coordinate is not in angle in quadrant 1. This is in quadrant 2.
Let me tell you why that is significant. Because this side of this triangle is negative. So yes, triangles can have negative side lengths in trigonometry. But if you do the Pythagorean theorem, you're going to square this 3, which is going to get you that 9, and you're going to square this negative 5, which is going to get you that 25. Which means that your radius, oops, I spilled the beans and told you what r stands for and why I've been using r. It's the radius of a circle that is centered at 0, 0. It will still be the square root of 34. And now that I have told you that is the radius of a circle, I can explain to you why I didn't ask you about plus or minus. The radius of a circle can never be negative. That is why I don't care about positive or negative. So, because the radius of a circle is never negative, the hypotenuse of your triangles will never be negative. We clear on that idea? Awesome. But x and y, they can be negative. Oh, and you know what else is really kind of a big deal? You might have noticed I didn't put theta on this picture yet. It says it's in standard position, yeah? And where do all angles in standard position begin? Where? Which axis? Which side of the x-axis? To the right. This is theta. We're about to do trigonometry on a triangle that has a negative side length. And we're going to do it at angle theta. And this theta is not even inside the triangle. And that's okay. So sine of theta is opposite over hypotenuse. But theta is not inside my triangle. So what do? What we do is we use a reference angle. This is important vocabulary for you. A reference angle. This is the reference angle, and I won't ever put a dot there again. I'm just showing you because for good note taking. When you go to do your opposite, your hypotenuses, and your adjacents, you are saying, if I were right here, what would be opposite me? If I were right here, what would be adjacent to me? And if I were right here, what would be the hypotenuse? So you reference this angle for opposite, adjacent, and hypotenuse. Cool? All right. Sine of theta then, opposite over hypotenuse. You pretend you're standing here, and your opposite side length is 3. Your hypotenuse is root 34. If you know sine of theta, you also know cosecant of theta. All you have to do is flip the fraction over, like so. Cosine of theta, adjacent over hypotenuse. If you were standing right here, your adjacent side is negative 5 over root 34. I like my fractions to have the negative sign not the numerator or the denominator. I like them in the front of the fraction. But Mr. M, then how do I know which one is negative, the 5 or the root 34? Well, that's easy, because cosine is adjacent over hypotenuse, and hypotenuse can't be negative. Guarantees to you that x is negative. Okay? Secant is the reciprocal of cosine. So negative root 34 over 5. And the last two. Tangent of theta, opposite over adjacent. One of those two numbers is negative. That means the fraction is negative. Negative 3 over 5, and the reciprocal, negative 5 over 3. Okay, now this produces a conundrum for us. If I gave you no other information, and I just said to you, hey, tangent of theta is negative 3 over 5, what quadrant am I in? Your answer would be, there's two different options, because I don't know if opposite is negative or if adjacent is negative. Because it's not both. Because if they were both negative, then it would be positive. Oh, that's an issue too then. If I told you that tangent or cotangent was positive 3/5, and I said, where am I? You still wouldn't know. Because they could either both be positive or both be negative. Because if you divide two negatives, you get a positive back. So we don't have that problem with sine, cosine, secant, and cosecant because they involve the hypotenuse. And the hypotenuse can't be negative. Well, or do we? Because the last time I checked, this 5 is negative in quadrant 2 and 3. And by the same logic, if I was down here, my y value is negative, and y is negative here and here. What I'm getting at is, if all you know is this, well, this is enough information to tell you because you can see sine and cosine and tangent. But let's just say I was like, hey, where am I? You might need more information. You know, okay, that definitely happens in 2 quadrants. That definitely happens in 2 quadrants. That definitely happens in 2 quadrants. You need more information. Okay? In first period, someone asked me, what if all I knew was that my hypotenuse is root 34? How would I know what quadrant I'm in? And I said, well, you wouldn't know. You would have to be told. You know, like for example, I tell you that this number is 3, and you know your hypotenuse is root 34. Is 5 positive or negative? The answer is yes. It's positive or it's negative. You don't know. You'd have to be told. So you need more information, or you have to draw 2 triangles when we do a lot of this stuff. You have to think about the 2 places where those scenarios could occur. And to make all that a little bit, in my mind, clearer, stop using SOHCAHTOA. Let it go. Don't use it anymore. Use it until you don't need to anymore. Master the better option. Because there's a lot of trigonometry that simply doesn't work if this is all you know. So what else would you do then? Boop! Since these things are in the coordinate plane, the xy axis, don't say opposite, adjacent, and hypotenuse. Say x's, y's, and radii, the radius. Because every coordinate in the xy plane can be written in x comma y. You could drop a vertical line straight down, and now you have a right triangle. And in this right triangle, you guys have already told me, you realized real fast that this has a length of 5. That's the x value. You realized real fast that this had a length of 3. That's the y value. Oops. And everybody remembers the Pythagorean theorem, right? If you do the Pythagorean theorem here, what you get is x squared plus y squared equals r squared. By the way, that is the equation of a circle that is centered at 0, 0. You should have learned that in geometry. A lot of people in first period didn't. They said they didn't, which means you didn't get far enough. This is the equation of a circle centered at 0, 0. So instead of saying sine is opposite over hypotenuse, say it's y over r. Instead of saying cosine is adjacent over hypotenuse, say it's x over r. And instead of saying tangent is opposite over adjacent, say it's y over x. And the sooner you master your x, y, r rules, the better off you will be. Try this weekend to spend time memorizing x, y, r. Thank you, nerds. I appreciate it.